Welcome back to the Python programming series. Now, in our last module, we explored error handling, learning exactly how to stop our programs from crashing and making them nice and stable. But today we are crossing a major threshold. We're moving from basic coding straight into real-world software development. You see, almost everything you'll encounter in massive Python projects relies on pre-written libraries. Whether it's doing complex math, generating random numbers, or fetching data from the web, this is where Python truly becomes a superpower. Let's dive right into this explainer on modules and libraries. To really understand Python's mindset here, we have to look at its underlying philosophy. There's this legendary software engineer named Tim Peters who wrote The Zen of Python. It's basically a collection of guiding principles for writing Pythonic code, which you can actually read by typing import this directly into your Python interpreter. It's a fun little Easter egg built right into the language. And this specific quote really hit the nail on the head for me, namespaces being a honking great idea. Organizing code into distinct, separated spaces is literally the entire foundation of what we're discovering today. So here is our roadmap for today. 1. Welcome to the toolbox. 2. How the import system works. 3. Mastering import syntax. 4. Hiding complexity with modules. 5. Future imports and packages. And 6. Recap and mini challenge. Let's jump right in. Section 1. Welcome to the toolbox. I really want you to think of a module as a developer's toolbox. I mean, when you're building a house, you wouldn't forge your own saw from scratch every single time, right? So why write complex math algorithms from scratch? Technically speaking, a module is just a basic organizational unit of Python code. It's simply a file containing reusable tools. Behind the scenes, it features a namespace implemented by a dictionary, which maps names to the actual code. Python already comes with so many built-in toolboxes, like ones for math, random numbers, and dates. You just have to pull them out when you need them. Section 2. How the import system works. The import statement might look like one simple command, but it actually combines two very distinct operations under the hood. Python first has to find the code, and then it has to bind it. Step 1 relies on two conceptual objects inside Python called finders and loaders. A finder searches locations like your file system paths or zip files to locate the module. If it finds it, it passes it to a loader which actually executes that module code. Then comes step 2, the binding phase. This is where the results of that loaded code are attached to a name in your current local scope, so you can actually type it out and use it in your program. Of course, things don't always go perfectly. Tying this right back to our previous module on error handling, if Python's finders search through your system and simply cannot locate the module you've asked for, it's going to raise a module not found error. Now, this usually means you either misspelled the module name or you're trying to use an external library that hasn't been installed into your environment yet. For instance, Python supports amazing external libraries for web scraping, APIs, or AI models. But if you try to import a powerful external tool like requests, you first need to install it using a package manager like pip before Python's finders can locate it. Moving on to Section 3. Mastering import syntax. Let's break down the exact syntax we use to bring these tools in. The first way is super simple. Writing import math brings in the top-level math module. This lets you access tools by using dot notation. So if you write math.sqrt with 16 in parentheses, it calculates the square root and outputs 4.0. You can also rename a module right as you import it, like import datetime as dt, which just gives you a convenient, short name to type out in your code. Finally, you can extract specific parts using the from keyword, like from math import sqrt. The distinction here is absolutely crucial. Saying import math brings the whole toolbox into your workspace, meaning you have to explicitly open it to get a tool, typing things like math.ceil or math.pow. But if you say from math import square root, you're reaching in, pulling out that specific tool and putting it directly on your workbench. You can just type square root without ever mentioning math again. It keeps your code so much cleaner when you only need one or two specific items. You can do the exact same thing with the random module to pull out tools for making random choices or shuffling lists. Section 4. Hiding complexity with modules. As you start using all these modules, you'll quickly notice they are incredibly easy to use, even though the code making them work is massive and highly complex. I was totally fascinated to learn how Python hides all this. It uses a really clever architectural style called the Pythonic PIMP. PIMP stands for Pointer to Implementation. In Python, it essentially means the library gives you a lightweight, easy-to-read public interface, but secretly forwards all the heavy lifting to a hidden internal object, which is often named with an underscore to tell developers to leave it alone. This creates a beautifully clean separation of concerns. The public API is what you actually see and interact with when you import a module. It's clean, well-documented, and very stable. But behind the scenes, the internal implementation is doing all the dirty work. For example, when you use the datetime module to fetch the current year or use socket for networking, you are interacting with a clean Python interface. But silently, it delegates the complex low-level execution to hidden C extensions to make sure it runs incredibly fast. So why does this matter to you? Well, because this exact pattern is what makes Python so incredibly robust for real-world development. By separating the interface from the implementation, library creators can completely rewrite their algorithms, swap out backends for faster versions, or even delay loading heavy dependencies until you actually need them. And the absolute best part? Your code never breaks, because that public API you imported remains exactly the same. Section 5. Future imports and packages. Now, what happens when you have hundreds of modules? This is where packages come in. A package is simply a special kind of module that contains a .path attribute. You can think of a package just like a directory on your computer, and the modules are the files inside that directory. Packages allow developers to organize massive amounts of code hierarchically, using that same dot notation to navigate through sub-packages and modules. Just remember, all packages are modules, but not all modules are packages. Before we wrap up the core concepts, there's a really unique type of import that feels a bit like time travel. It's the __future_ import. Now, this isn't a normal module at all. It's actually a special directive to the Python compiler that lets you use syntax or behaviors planned for future versions of Python right now. It's just a brilliant way the language allows developers to test out upcoming language features and migrate their code safely without everything breaking at once. And finally, Section 6, Recap and Mini Challenge. Let's recap what we've covered. Modules are your reusable code toolboxes, packed with built-in functions for math, dates, and random numbers. The import system uses finders and loaders to search for code and bind it to your local namespace. Your syntax, like import versus from, strictly controls what enters your workspace. We learned that modules often use the pimple pattern to hide incredibly complex C code behind simple Python interfaces. And finally, packages let you group those massive projects together, while external libraries from pip open up a whole new world of possibilities. To finish up today, here is a mini challenge to test your brand new skills. I want you to create a program that generates a random number between 1 and 100, prints the square root of that exact number, prints today's formatted date, and then randomly selects a fruit from a list of 5. You're going to need the random, math, and datetime toolboxes to pull this off. Give it a try. In the next module, we're going to build a mini project combining everything you've learned so far: variables, loops, functions, and files. This is where Python starts feeling like real software development. Keep going. You are building real developer skills now. I'll see you in the next explainer.